In this video, I'm going to talk about binary search. Binary search is a search algorithm that works on sorted sets of data, which is important. These data sets need to be sorted for binary search to work properly. So if I just come up with a random example here, something like this. The way that binary search works is the goal of this is to determine whether or not a given number exists in this set. So you may be asking the question of, does 6 exist in this array or in this set of data? Or does 12 exist in this set of data? And binary search essentially splits the data in half with this knowledge of being sorted with each iteration that it does on the data set. So to start, what binary search does is it looks at the midpoint. So if it takes the total size of the array, this one is 7, and it looks at the midpoint. And for odd numbers, it's really easy to see which number is the midpoint. There's 3 on each side. For even numbers, you can pick either one of the two. For a odd number size, we'd pick this number 7, and we'd say, here's 7. And we would check, is 7 greater or less than our target value? In this case, 7 is greater, which means we know that if 6 exists in this array, we just need to look on the left side. So the next thing we do is we explore this section, this sort of subsection here of 2, 3, 5. And then we would look at the midpoint again, which would be 3. And we'd say, is 3 less than or greater than 6? It's less than, which means that we need to look on the data on the right. And then we look at the data on the right of the 3, we're down to one value, which is the number 5, and we do a compare, is 5 equal to 6? And our answer is no. Now the interesting thing about this is there's 7 pieces of data here in our data set, but we only had to do 3 comparisons, 1, 2, 3, to determine whether or not the 6 existed in this data set. This can only be done on a sorted data set because we know when we compare it against a mid value like this that we know if it's either going to be on the left side or the right side just based on how we're comparing this value, right? 6 is less than 7, so we know it's the left of the data set. If we look for another value like 12, is 12 in this data set? Then we would start in a very similar way. We would say, we'd start by looking at the midpoint. We'd say, is 7 greater or less than 12? We would say 7 is less than 12, which means we need to look at the right side. We would then look at 9, 12, 22. And we would compare 12 to 12. And at this point, we know that the value exists. We found the matching value. In the same exact method here, we're also going to do at most 3 comparisons. This algorithm ends up being big O of log n, which means that as our data set grows, this algorithm actually doesn't get too much more complex. If you think about it this way, if we were to give this thing a data set that was a sorted set of numbers, 1, 2, 3, dot, 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 all the way up to the value 1 million, right? We had this array of 1 million elements, and we were searching for a value in here. If we suddenly doubled the size of this array and said that this thing continued until 2 million, well, the differences in the number of comparisons we need to make is actually only 1. We doubled the amount of data within this array, but because we're splitting it in half each time by checking against a midpoint, we only increase the number of comparisons here by 1. So our 2 million element array, we do 1 comparison with the middle value, which may be this 1 million number, and then we'd look at just 1 million elements. And so suddenly after only 1 comparison, we split our data in half. That's how we get this log n runtime here. And this is a fantastic way to search through a set of data looking for an individual value.